Hello, today we're going to talk about energy. This is the first recording that I'm doing for your class, and hopefully you've already done the Gizmos lab on energy, and then today I'm going to give you the introduction to energy, and then you should already have the paper of questions on energy. Otherwise, I will also include it here on Canvas. So let's start talking about energy. So what are the different types of energy? We have heat energy. Oh, this is not going right. There we go. This. Okay. We have heat energy, which is also known as thermal. What else do we have? We have light energy, which is also, some people call it solar, some people call it radiant. Maybe what else do we have? We have chemical energy, energy stored in chemical bonds. We have mechanical energy. Some people would consider sound as part of that. Okay, so mechanical energy is like a water wheel moving, us turning the pedals to make the bicycle go, or whatever. Those are all mechanical energy. What else do we have? We have electrical energy, electricity, the movement of the electrons. And we have nuclear energy, the energy stored in the nucleus of atoms that when we disrupt that releases a tremendous amount of energy. So those are the different types of energy. And then potential and kinetic are not types of energy. They're kind of like the overall, all of these could either be in their potential form or their kinetic form. So potential means stored energy. So for instance, with when you eat something, energy is stored in the bonds of the carbohydrate or protein or whatever. And then when your body digests that and breaks it down, then that energy gets released. That would be in the kinetic form when the energy is being used. So potential stored energy, kinetic is energy in motion. And we have the classic statements about is this an example of potential energy or kinetic energy, like water at the top of a waterfall? Okay, well, that would be potential. Okay, if it's just sitting there at the top. Kicking a ball, that's motion, that's kinetic. Energy in the lump of coal, that's stored in there, that's potential, until it's actually being burned, and then it would be kinetic. And the other one on here is an earthquake, that's kinetic, that's motion. Okay, so whether it's energy actually in the process of being used, energy of motion versus stored energy. When energy is released by a chemical reaction, that's exothermic. That means the energy is going out and it's going to feel hot. The substance is actually losing energy. The energy is going out. Exo means exiting. And we have seen that in lab where you've done a reaction and it got hot. Okay? And that would be when you, for instance, put the magnesium in hydrochloric acid, that got hot. The other type of reaction that we can have is endothermic, and that's when energy is getting absorbed by the reaction, and then it will feel cold. So I put red for hot, blue for cold. With endothermic reactions, energy's actually going in, but it's being taken from the surroundings. So what you're feeling in a reaction is the surroundings, like the test tube. And you will feel cold. It will feel cold to you if it's an endothermic reaction because it's taking energy in to make the reaction happen. Whereas when it's exothermic, the reaction itself is losing energy, and the energy is going to make the surroundings heat up. A cold one would be if you dissolve baking soda in water, it will get slightly colder. It'll feel cold. If we were here in lab, we would do like ammonium nitrate in water or ammonium chloride in water, and it would feel very cold. So if it feels cold, it's because it's taking the energy from the surroundings, from the test tube or the beaker. If it feels hot, it's because it's releasing energy to the test tube or the beaker. An example of an endothermic process is anything where heat's being put in to make it happen. So like an ice cube melting, heat has to go in to make that ice cube melt. Anytime you're taking a solid to a liquid, anytime something is melting, that's endothermic, heat's going in. Also, to make something go to a gas, like either just to evaporate or to boil, heat has to be put in, and that would be an endothermic process. If heat is going in to make it happen, that's endothermic, in, endo. Okay, in, endo. An example of an exothermic process, now heat has to be taken out to make it happen. So that would be like a liquid going to a solid. So freezing, heat has to be removed. Now the thing that's a little bit confusing is when something freezes, you're feeling it get cold, the end result is cold. Okay, so, but heat was removed to make that happen. So it's an exothermic process if heat has to be removed to make it happen. So in this case, don't worry about what it feels like. You have to think, do I have to put heat in to make this happen, or is heat being removed to make it happen? With burning, that would be a exothermic process. Okay? Heat is being given off, heat is removed. Energy is always required to be put in to break bonds, and when bonds are formed, energy is released. So if the bonds are stronger in the reactants, then more energy has to be put in than will be released. Okay, because again, energy has to be put in to break bonds. Energy is released when bonds form. So in a chemical reaction, if you have to put more energy in than you get out by the products, then that reaction is endothermic. So if the reactant bonds were stronger, more energy has to be put in to break those bonds, to get that reaction to happen, then will be released when it's formed. So overall, it's like a deficit of energy. Energy had to be put in. We can show this with an energy diagram. And an energy diagram is where we're going to have energy versus time. So the reactants are going to start at some level. Let's say we had A plus B. Okay, so our reaction is A plus B makes AB. Okay, so our reactants start at a level. Well, there's something called an energy barrier that the reactants have to be able to overcome to actually react. So they're colliding, the A and the B molecules. And if they can overcome this energy barrier is called the activation energy. Okay, activation energy. So it's like if you were starting at the bottom of the hill and you had to make it over to get to wherever you were going, that's what this is. This is this barrier, this hill that they have to make it over. If they have enough energy to make it over that, they will go into what's called a transition state where they're starting to come together to make the product. Maybe some bonds had to be broken as new bonds are forming. Maybe this was really a 2, which means that an A and an A are bonded, and that has to be broken, and then to form the B and the B. So those have to be broken as new bonds form. So that bond has to be broken, that bond has to be broken, new bonds form. Then when they are successful to become products of A, B, that is actually higher in energy than when they started. So the difference between where the reactants were and where they end up as products, that's the amount of energy or heat that was absorbed. And when energy is put in, absorbed, we give it a plus sign. Okay, so heat, delta H is heat. We're going to give that a plus sign. That's a positive amount being put in. So in an endothermic reaction, the reactants start at a certain energy level. They're bouncing around, colliding with each other. If they can make it over that hill, that activation energy hill, then they can go on to become products. But if they end up higher in energy than where they started, that's the amount of energy that's absorbed. And that is endothermic. Okay? Endothermic. Heat went in. They absorbed that much energy. So this is my drawing that I drew before. The energy level, the reactants started here. They had to make it over the activation energy, and they ended up higher in energy than when they started. So the difference is how much energy was absorbed. And it would feel cold if we were doing this in a beaker and we were filling the beaker, it would feel cold to us. So the key is that delta H is positive because the products ended up higher than where they started as reactants. That amount of energy was absorbed. The opposite of that is for an exothermic reaction. So for exothermic reactions, still the reactants are starting at a certain energy level. They have to still make it over the activation energy barrier to get to this intermediate transition state. But when they form products, they drop all the way down lower than when they started. So this amount of energy is the amount of energy given off or released. So it's given a negative sign because energy was released. If we do this in a beaker, it's going to feel hot to us, or warm at least, because the energy given off will heat up the surroundings. Sometimes the change in energy isn't very much, but it will always be something. It might just be barely changing, but it'll be something. So a lot of times when we do them, we don't really feel them getting hot or cold when we're doing it in a test tube or beaker because it's such a small change. But it either has to have energy being absorbed or given off when we're doing a chemical reaction. And we can actually put a value on that energy if we measure it. And in our units, we either use joules or kilojoules or calories for heat. So in this case, we could say heat was produced, that amount of heat that was given off was produced, it would be on the product side. I just made up this number, let's say it was 250 kilojoules given off. So we could write that as a product, or it's given a negative sign when it's given off. So delta H is negative or given off, it's a product when it's exothermic, and delta H is positive, or it would be on the reactant side of the equation if it is endothermic. One too far. So again, our units are either going to be calories or joules for heat, and 1 calorie is equal to 4.184 joules. You need to know that conversion. 1 calorie is 4.184 joules. So we can just use that like all of our other conversions. Okay, or we can flip it, 4.184 joules is 1 calorie. If we have kilocalories, that will be either capital CAL or it'll be a KCAL for kilocalorie. That's what 1,000 calories is. And if you look on food labels, the value that they give on there is really the kilocalorie, not the little calorie. So if you see that you're eating something that has 100 calories, it's 100 kilocalories or 100,000 little calories. So they should on the labels be written with a capital C, but most of the time not. They're written as a little c. Okay. People don't want to have those big numbers in there, I'm sure. When you go to eat that bag of chips or candy bar or whatever, you really don't want to see 3 extra zeros on the amount of calories. Okay, so a nutritional calorie is really 1,000 calories. And then with joules and kilojoules, 1,000 joules is 1 kilojoule. So we could convert between kilocalories and kilojoules. Here, 1 kilocalorie is 4.184 kilojoules. Okay, but remember that 4.184. So in your conversions, if you're going to convert 25 calories to joules, 25 calories, and then our conversion is that 1 calorie is 4.184 joules. And we would just multiply 25 times 4.184, which is, calculator, 25 times 4.184 comes out to be 104.6 joules. Or if we were going backwards, converting 5,500 joules to calories, then we would say 4.184 joules is 1 calorie. So we would be dividing 5,500 by 4.184, and that would be 1,315 calories. We could also convert in between nutritional calories and regular calories, because again, nutritional calories are kilocalories. So if we had 450 nutritional calories, okay, to convert that to calories, there's 1 kilocalorie is 1,000 little calories. So it would be 450,000 little calories. If we were going to convert that to kilojoules, then 450 kilocalories or nutritional calories to kilojoules, it's still 1 kilocalorie is 4.184 kilojoules. Okay, and in that case, it would be 450 times 4.184, and that would be 1,883 kilojoules. Okay, and that is as far as I'm going to go today. So we will stop right